Everybody, welcome to the Geology Research Talks for 2021. Ryan is our first speaker. Ryan Mathur is our first speaker for this year. We'll have a whole series of talks lined up for late in the year as well, so I hope you'll keep an eye on our adverts. Ryan, we are very fortunate that Ryan is speaking to us today. Ryan is, I don't know what I should say, this morning or this evening. I suppose, Ryan, you're speaking this evening?
Yeah, it's tonight, yeah.
Last night?
Yeah, that's right, yeah, last night, exactly.
So Ryan is a world expert on metal isotopes, and we've been working with Ryan here at James Cook University for the last 2 years in a few exciting projects exploring the use of metal isotopes in mineral exploration. And since Ryan has been working with us, I suppose he's been developing a nightlife. And it's been very exciting. There's lots of new opportunities that are clearly arising in this field, and we're very fortunate for Ryan to give us a bit of an introduction on how metal isotopes can be used in mineral exploration and how they can be used in characterizing mineral deposits. Ryan is a lecturer, a professor at Juniata College, which is a small private college in Pennsylvania in the eastern United States. So there's a bit of a time difference, a time gap between where Ryan is at the moment, where we are here in Australia. And I believe that our audience is quite international as well. So we'll have people listening in from all parts of the world at all sorts of times. But anyway, Ryan, over to you. And we look forward to an interesting talk.
Okay, thanks, Paul. So like Paul said, today I'm gonna hopefully get this into presentation mode here. Is it gonna make it? Let's try again. There we go. All right, so today I will talk about how we use metal isotopes in a variety of ways in ore deposits, and I'm going to focus in on two different ways. And I put that in the title. The first is sort of how these deposits form and why it's important that we look at the isotopes in this way. And then the second way will be how can we explore using sort of these different new isotope systems. And the work that I'm going to show today, this certainly isn't my own. There's a lot of people who've done this, and I'll have acknowledgements at the end, but I sort of going to give you highlights of what we do and what I think is interesting and new. So I won't necessarily be talking about a lot of published things, but things that sort of are up and coming and almost out there. All right, so I've designed this talk in two ways, as the title suggests. Is I'm going to try to explain to you how I think comparative analysis in these isotope systems can reveal some very interesting things associated with process, and specifically source and how that is related to making a metal deposit. And I hopefully will provide information so you'll understand why it's important to look at these isotope systems, not only when you're exploring, but in known systems, so that we can understand the known systems and then apply that data also then into the unknown systems. So I think there's a lot of new avenues and ways of thinking and comparing the data sets that we're just starting to realize, because a lot of this information is just being gathered right now. So I think I'll start with that, because I know there's a lot of working with a lot of different mining companies. Sometimes there's hesitance and wondering, why do we want to look at something where we already know the metal is? And I think it's important, and I want to show you why. And then the second thing I think has a great potential in exploration, it's been used in several places, is vectoring. And I'm going to specifically use copper and water, because we have some really exciting results that I want to share with you from some work we've been doing in Australia. And I think it really demonstrates the true potential of looking and using this sort of analysis in ore deposits. So what elements are we going to consider here? We're going to focus in on copper and zinc. I don't know if I'm going to have time for silver. I put that in the title, but I'm going to try to get there, but I doubt I will, because I tend to talk a lot, and I'll try to get there if I can. We've also done a lot of work in tin and antimony, and I'm not going to spend that much time on there. There's also other transition metals and metals that have been used, titanium, vanadium, chromium, iron, and nickel. I won't spend there. And I will spend a little bit on molybdenum. And I think there's some very interesting and fascinating results coming out of a molybdenum rich belt in China, which we've been doing work for there too for a while. So these are the ones I'll focus on, and you'll note that these are all stable isotopes, and that we're going to work with, and the values will be presented in per mil values. And so the way that you can think about these, if the values are higher or positive, that means they have more of the heavier isotope in them. Then if they're negative, then they have more of the lighter isotope. And so I give the example here with the units with copper. So I mean, everyone's traditionally associated, I mean, understands if look at oxygen, sulfur, the metals are the same. And traditionally, most of the isotope geochemists will put the heavier isotope on the top so that positive values mean enrichment in the heavier isotope. Sometimes it changes depending on what labs, but most of them do it this way. There's international standards. And so I usually use NIST standards that have been developed that I compare to, and they're internationally recognized. We also developed in-house standards for a lot of these to confirm the QA/QC and the quality of the data. And most of the time, mass bias is controlled by bracketing at some sort. And with certain elements, we'll also dope them with other elements to make sure that we're attending to mass bias and correcting what the instrumentation can do. And I'll have a lot of the errors here. You can think of most of the errors on this are around 0.1 per mil for copper. Zinc is a little bit lower, is around 0.05. That's a 2 sigma, the error there. And molybdenum is also a little bit lower, around 0.0607, something like that. So the errors are relatively small in comparison to the variations that I'm going to show you. And the errors have been determined by running multiple samples and looking at the standards throughout the runs. So there's been a lot of sort of background measuring stuff that I'm not going to cover at all, but it's certainly very important so you can get sort of meaningful data. So the first study I want to talk about is something we've been doing, working in some copper isotopes and looking at mantle rocks in Canada. And Graham Pearson and a lot of the people and a lot of his students have been working on these mantle rocks. And we looked at Hendrik Falk is the person here that sort of started this. He asked the question if, you know, he's reading some articles about copper coming from the mantle, and then the question becomes well, can we use the copper isotopes in the mantle to see the source of metals on surface, and can you make a relationship? And one of the biggest questions with the copper isotope data and a lot of these metal isotopes data is, well, how do we interpret them, and how can we use them? I think a lot of people have a great sense of using the copper isotope values, and they change, and we can use them to vector and the ore deposit. But is there an element of source that we can deem or we can somehow tease out of these data sets to try to link the metal source in some of these deposits? And so Hendrik basically was curious about this and got us connected and sort of started this project. So I'm going to show you about this project and some of the results, at least how I see them coming out right now. We're still in the writing process here, but I think this is interesting. So we looked at peridotite and lherzolites that were coming from some kimberlite pipes and in here in southern Canada. And the two we chose were Wawa, which you can see are relatively older mantle, I should say older extrusions, one way of thinking about it. And then we have something that's younger that are kimberlites in Kirkland Lake. And so we can compare. What's interesting about this sample set is that we have a sort of an older perspective of the mantle and then a younger perspective. And what's been interesting about the Kirkland Lake data, people have been working with, this is just copper concentration if you focus on the left, and depth of where they got these rocks out of. As you can see at the base of the lithosphere here at about 150 or 160, you can see there's a distinct increase in the amount of copper concentration. So the question is why is this here? And the argument might be copper is somewhat temperature dependent, but I think a more, and if you do some of the, there's a lot of other plots that I could show you here that sort of argue for that this is a metasomatism that exists at the base of the lithosphere here. And what's interesting here is that you can see that there's a clear concentration increase at the base of the lithosphere. So there's been a metasomatic event that sort of enriched the lithosphere, and we're wondering, you know, sort of what happens with copper isotopes in this enrichment process. And, you know, we also think in these ore deposits a lot of times is, do you have to do something to the mantle first, and then it gets fertilized, or however you would like to describe it, and then ultimately that metal then ends up in ore deposits as they ultimately end up at the surface. So we can perhaps use the copper to trace that process, and that's what we're doing here. We also looked at zinc, and in this instance, zinc isn't really telling us so much, so I'm not going to focus too much on zinc there. What is interesting is that if you look at the Kirkland Lake samples where you had clearly metasomatic event, is that if you get deeper into the lithospheric mantle, the copper isotope values show a relative increase, and it gets significantly higher. And there, it's not a perfect linear relationship. I totally understand that, but it does seem that there appears to be some sort of lower to higher copper isotope value as you get deeper into the mantle. And so does that suggest then that these metasomatic events lead to induction of heavier copper into the lithospheric mantle? And there's been some suggestion of that. Liu was the first one to write about this in 2015 in his paper, where he established the bulk silicate earth value of around plus 0.6 per mil or 0.06 per mil. And he did look at some metamorphosed mantle rocks and did see some higher values in them. And there have been several other articles since then that have also tracked this sort of change. And so if we look at this, as I said, we have this sort of older versus younger, and that younger event has been metasomatized. And you can clearly see, if you look at, we don't have a ton of samples, but the older mantle, one way of saying it, sort of sticks around what you would think at around 0 per mil. And then after metasomatism, you can see that there's been a distinct scattering of the copper isotope values. And once again, in the metasomatic part where the copper is enriched, you sort of see that heavier copper isotope value emerge. And I just showed you here these green dots. I know the copper isotope value isn't labeled on that x-axis there. I just want to show you the distribution of the data. There's not a lot, but there's certainly some. And I think it's important that you see this difference between the older and the younger metasomatized mantle. So there's osmium data and a lot of other interesting ways that we can link this. And on the plot that I've got here, I've got copper isotope value versus osmium. But I point this plot, I think, is very interesting because if you look at, as I said before, you go deeper, you get sort of these higher values, and that's that blue arrow right here. And you can get up to 0.2 and to 0.5 per mil copper. And what's fascinating is that if you look at the mean value of the Michigan copper deposits, which are classic, the Keweenaw right in there, there's a data set there that exists that I've measured some and a lot of others, about 200 copper isotope measurements, relatively tight, that forms right around 0.2 to 0.3 per mil. And then equally interesting, we looked at some gold, some copper and gold from Kirkland Lake. And that is also showing slightly heavier at around, not at a mantle value, but around 0.2 or so per mil. And so this is very interesting because, if we pinned a process where we see a metasomatic imprint in the base of the lithosphere, and that matches what we're seeing in the ore at the surface, I think that's a pretty interesting observation, because if you want to talk about source, the missing component there is obviously transporting the metal from the base of the lithosphere up into where we have it on surface, but the similarities in the matching of a metasomatized mantle and the ore that sits on surface, I think is a pretty nice match, because we're actually using the metal. We're not using other metals like rhenium and osmium and then inferring similar relationships. Here, we're actually just looking at the metal and comparing it to the metal. So that's why I think it's quite a fascinating relationship. Now, I don't know, is it 100% guaranteed? This is a great interpretation. I don't know, like I said, because we still have to transport the metal from the source to the surface. And then, as I'm going to show you here, there's going to be other processes that can ultimately lead to fractionating and changing the copper isotope values as the deposits are forming on surface. So how can we use then, if this source business is true and is something to chase, how can we look at these data sets and what can they tell us? So what I've got here are, these are violin plots, and think of these as sort of sideways histogram plots that are mirrored right down the center. And the reason I like these diagrams is because it shows the spread of the data, and it also makes a quick comparison, and it's a little bit better because than the box and whisker plots. I just think it looks a little more artsy, so I enjoy them. But they more or less get across the same point. And so what I've plotted here, just for comparative sake, is some copper isotope values from, here I have classic said copper deposits, the Cooper Schiefer, Copes Lake. LA is a small deposit we've been looking at in Australia. And the DRC, that's some published values in Africa. And then I also compare those to other deposits that are also considered to be SEDEX deposits like Michigan and some of the work we've been doing at Mount Isa. And one thing that I find interesting when you look at these plots is, you look at the mean values and the basic distribution of the data. You can look at the Michigan and Mount Isa, they're relatively tight and their means are higher. And in comparison to what's happening to Cooper Sheeper and Coates Lake, they're much greater spread and the means are actually lower for the copper isotope values. So what does the mean mean, I guess, in this instance is what I'm after. And if you then look at, and here's a mean of porphyry copper data, which is epithermal systems, and this is data, these are all from chalcopyrites. We're not looking at any sort of secondary process here in the porphyries. This is all the high temperature chalcopyrite data. And one thing I find interesting about this plot is that if you look at the means of Michigan, Mount Isa, and the porphyry coppers, they all slightly sit above 0, or the bulk silicate earth value. And so it makes you kind of think when you see these things, is this, even though there's a large spread of the data, and you can see these violin plots, the tails and the bulk and the modal distribution in them tell you things, but I think, if you look at it this way and you say, well, those means are slightly elevated, and does that represent perhaps metal that's coming from these systems in lithosphere or mantle that has been somehow have some oxidized copper or something like that, and is it evidence of this sort of fertilization process that might be happening and might aid in the generation, or be a key to making these deposits? And I think when you start thinking about these deposits in this way, I think in this comparative sense, and as all our data sets start to grow, I think you can have some really quite powerful analysis and ways of comparing. It's not, it goes a little bit, I think, more beyond than just saying, okay, these isotope values shift in a deposit and can perhaps be used for vectoring. I think you can sort of try to see the forest among each one of these deposits, or trees that sort of sit there, and try to compare them. Same thing can be done with zinc. And here I've got some SEDEX deposits, but here I compare different deposit types, or what are classified as different deposit types for, and I'm gonna show you some stuff from the first box there in the SEDEX, or Grenville SEDEX deposits that have been metamorphosed here in the northeastern United States and in Canada. Red Dog, that's some published data from Alaska, and then Mount Isa, like we've been working there. And then the MVTs and the VMSs have all been previously published by several different authors. And if you're interested in that data, of course, I can point you in those directions. But I think when you look at the plots in this way, one thing that you can kind of look at the zinc data is that you can see that the MVT and VMSs sort of have a much greater spread than the SEDEXs. And I think that might speak to process, and perhaps is related to zinc volatilization. And maybe that's a factor that's more prevalent in these perhaps different types of systems that where zinc could be fractionated. Now, there's a lot of other potential explanations here, but I'm just sort of giving you ideas of why I think this stuff is interesting, and how it could be related, and how you can compare these things, and what sort of information you can gather. So another project we've been working on are looking at the zinc deposits in my neck of the woods here, sort of north of where I'm at. And these all formed in the Grenville provinces, and they're mostly in, as you can see, the deposits that William Peck, he was the one who drew up this map for us, and basically provided the majority of these sphalerite samples from these SEDEX deposits. And then it shows you some that the majority of the stuff that we're looking at more or less lies in Canada. And we also, the impetus behind this was we were looking at zinc isotope fractionation in the really strange minerals, the zinc oxides like franklinite and willemite in New Jersey. And a lot of places, I measure a lot of these things at Rutgers. And so we had a lot of interest of trying to do something local and understand sort of what's happening with these deposits, and why are these zinc oxides here. And so to give you an idea, this is the new display here at the American Museum. This is a wall that was basically cut off with in Franklin Hill there in New Jersey, and now is on display. And in fact, our samples come right off of this wall, which is kind of funny if you think about it. But we have a variety of different phases that we looked at in the zinc oxides, and you can see some quite some interesting relationships. But one thing that we found with the data is that if you compare the oxide to the sulfide data in these settings, because a lot of people have argued, why are there zinc oxides here? Are they, residual or leach sulfides that became oxidized, or during the SEDEX formation was this basin simply had more oxygen, and so you're able to form zinc oxides instead of zinc sulfides that were forming off in the basins that more or less set to the west of what was happening in Franklin. And what's fascinating is if you look at the spread of the data here, again on the violin plots, the zinc oxides sit clearly higher than, on mean value, than the zinc sulfides. And so you can also relate this to bonding arguments, which I think are interesting because the zinc oxygen bond strength is much greater for heavier isotopes than that of the zinc sulfur bond strength. And so maybe we're seeing that play out in comparing the systems in this way. And so, you know, we've coupled this with also some oxygen and carbon data, and there's some other interesting trends in here. But I just think it shows you, you know, gives you an idea of how you can compare these things and sort of the process that it can help you illuminate and say what's sort of going on. All right, so another study where we're taking this approach and thinking about sort of a comparative analysis. So this is what I mean by when I say comparative analysis of these isotope values. And we did a lot of work on molybdenum deposits in the Qinling orogenic belt. And Yao Juming was the one who started this, and we were working there from about 2014 until maybe 2018, and we've done several trips there. And what's interesting about this belt is that it has arguably one of the largest concentrations of molybdenum on Earth, and there's also a variety of different types of molybdenum deposits there, from porphyry style to some really weird rocks, which I'll show you next, are these carbonatite veins, and that's what I've got here in this place called Honglongpo. And in here, these were the weirdest rocks I've seen in the field. They are carbonatite dikes, and you can see the carbonatites are clearly cross-cutting this intermediate metamorphic rock. And in the dikes themselves, if you look on the image on the right, excuse me, on the left, you can see molybdenite is occurring as a paint on the boundaries and the veins, but even in the center of the pegmatitic vein, I shouldn't say pegmatitic, carbonatite vein. If I was saying pegmatite, I should have been saying carbonatite. Sorry, it's late. The carbonatite vein has a bunch of sulfide in there too, so chalcopyrite and pyrite. So these carbonatites are clearly, you know, sort of shots out of the mantle, and these were really strange looking rocks. So I figured I'd show you some pictures of those too. So what do we see in the data set? Here are, once again, sort of a plot, and here we have box and whisper plot comparisons of molybdenum isotope values, both in molybdenites, host rocks, and the carbonatites, and then the calcites and the carbonatites. And what's neat here is that you can see in Honglongpo it has a clearly lighter molybdenum isotope signature in comparison to the porphyry systems laying in the same system in the Qingling Mountains. And then we have Dahutang, which sort of sits off farther to the east there, and it has a significantly heavier value, mean value when you look at these things. And so you can look at this and you know, you scratch your head a little bit and, well, what exactly is this, are these molybdenum isotope values showing us? And so you can take the comparison a little bit larger. And so then we compared to, as you can see here, some the other data in the literature. And so, you know, we have Dahutang, which is, like I said, further to the east, and we're calling that sort of a crustal end member. Also the stuff that was in Switzerland, and also some Tibetan things have higher molybdenum isotope values. And the carbonatite clearly has this lower value and sort of has this, what we're arguing, a mantle, more like a mantle type signature to it. And the way you can also see this is compare the molybdenum isotope values that we see in Qinling and then compare it globally. And that's what these histograms are showing you here. And you can see that there's an offset to the left where you have this sort of a lighter value that is appearing in molybdenites in the Qinling Mountains and also in Climax-Henderson and molybdenite. So you see this shift to the left where you get these lighter molybdenum isotope values. And we thought, well, they're related processes, and how can this happen? And it also might have to do with lighter molybdenum perhaps coming off the slab, because we know, if you look at this image here, the pelagic sediments, that's some of the lightest molybdenum on Earth sits in these things. And so perhaps when the slab subduction is happening, you can get lighter molybdenum sourced from the slab itself, some from the slab hydrating the mantle wedge there. And this perhaps might be another mechanism that we're seeing operating, at least in some of these molybdenum-rich systems. Now, we've been looking at these data and trying to figure out a clear path for interpretation. And this is just sort of one of the ideas that we were chasing down and thinking about perhaps explaining why all these values are sort of shifted towards lighter values in molybdenites. All right, and then so the last sort of portion of what I wanted to talk about today is spending some really new and interesting data that we've gotten from groundwaters in Jericho in Australia. And I want to preface the conversation before we go down this road that these are all sort of preliminary, and we're sort of trying to understand them as we're doing this, because I measured these, I think, in January. But the results are so fascinating that I figure it's worth sharing, because the uniqueness of them speaks to the fact that we really don't know a lot about these systems. And I think doing studies like this will really allow us to see the potential of what these values might ultimately be saying to us. So what the idea is, and why are we looking here? It's because we need to be able to find deposits that are undercover. And one of the ways of doing that is looking at water, and you use water as a probe to see what's in the subsurface. And I've developed, or we've talked about this technique in several other papers. I developed first in paper we published, this was in the Pebble deposit in Alaska, where, if you're familiar with that terrain, there's a lot of surface water that sits there as lakes and also seeps. And we found this very interesting relationship where the seeps that have heavier water or higher values were associated where the Pebble deposit sits. And the hypothesis that we think that explains this phenomena is that when you oxidize sulfides, you favor the heavier copper isotope, and that heavier copper isotope will go into solution. And so that if you look into solutions that have heavier copper isotope values in comparison to other them, you can infer that there's been weathering of copper sulfides. And we think that's a pretty good relationship. You can say, well, are there other processes that can lead to giving higher copper isotope values? We don't think so. We've looked at weathering of silicates and a lot of other different rocks, and sulfides seem to be this special case where the oxidation, because a lot of the copper sits in this copper 1, and in a lot of silicates, you don't see that. And of course, in copper oxides, you're already oxidized, so you're not going to induce much of a change. Okay, so the hypothesis that we started with is we think that if you're interacting with sulfide-rich rocks, you would generate copper isotope values that would be heavier wherever those are weathering. Now, I understand in groundwaters, the situation, there's usually not a high amount of oxidation potential, right? Because you're in highly reduced waters normally in groundwaters. And you'd ask Ryan, why are you suspecting that? And I said, well, there's probably still some oxygen, and you might still get be able to see the source. But we're just testing this out. And thank God, Helen and the people in James Cook that I'm working with agreed with me, and so we could try this out. And so it's nice because of a sampling. You can see a lot of the sampling sites were wells that farmers already have established, and then also wells that sat in the back of people's houses. And that's what these 2 images are. So it becomes a sampling of things that are already there. And you just have to obviously get permission to get the water, which sometimes can be problematic. But thank God Brandon was doing that, not me. All right. So when we first measured all of this stuff, I thought the mass spectrometer was broken. And I really thought that there's no way the values that I measured or were measuring at that time, I just couldn't believe them, right? And it was, I kept emailing Brandon, you can ask him, I said, there has to be something wrong here. These values are just ungodly, not right. And, but I kept measuring because, well, what else do I have to do? I got to report the data. So, we got these really strange values, and you'll notice that I plotted these on this histogram, and you'll see that it's the per mil copper, but the values are in like hundreds. And the normal range that people have reported for 99% of all the copper isotope data fall in this blue box that you can see right here. And you can see that this is like really, really different than anything else that's ever been measured on Earth. And so then I also compared it. I had done some work for First Quantum, and we looked at some data that I hadn't published that were actually kind of a little bit lighter. And I put those values in there along with some other values that were a little bit lighter and a little bit heavier. So I have that red box. So that's that other 1% outlying, I guess you could think of. So still, when you look at this, you think, good Lord, this just can't be right. So, there has to be some analytical issue. As an analytical chemist, that hat gets put on and you say, gee, these data are no good because, well, they just can't be. So first, maybe is there some instrumentation issue, or did I process the samples incorrectly? Because you got to purify the samples, the copper out of them before you measure them. Well, I ran a USGS rock standard, which is a basalt, ran perfectly well. And I also have an internal standard that I use as a copper penny from the United States here from 1838. That was right on the button. So the processing, because you process the rock more or less the same way you process the water, was done the same. Now the water admittedly had a little more sodium in it, but I'll get down to that in a little bit. But the chemistry processing seems okay, and the instrumentation seemed okay. The standard didn't really change that much throughout the whole system. Usually if you induce if there's some element that I'm not accounting for that's in the solution, the standards usually go crazy. And you'll see, up to 1 per mil to 2 per mil, even greater in the shift if you have some weird ion that you didn't anticipate when you're measuring. So I didn't really think that there's something in there that I couldn't have accounted for, because the standards more or less stayed constant. And so that's a pretty good indicator that you're not inducing a matrix in the plasma, which basically throws off all your measurements after the point that you run that sample. The voltage of the standards and the samples matched. And there were some that I had for 10 samples that I have, I said here, I had slightly lower voltages because we're working in parts per trillion here. So we had some smaller voltages there. And so I actually reduced the standard voltage so that they match all within 10%. So I can't really point to the standards and samples matching or some sort of linearity issue as being a problem. And then after that, because the numbers are so weird, we had small aliquots of the solution left. We actually checked them for sodium. Sodium can be, could potentially be a problem, right? Because when you're drying these waters down, you're getting a lot of salt. And sodium, if you add too much excess of one ion in solution, you could cause sorts of problems. But I didn't really find sodium greater than copper, than maybe even 1 or 2 to copper. So it wasn't, and that won't, we've done a lot of experimentations. You might get a standard shift of maybe 0.1 or 0.2 per mil with that sort of ratio. So I couldn't even find anything in the solution that I thought was wrong. And so, as I said, just to further test this, we did some other tests with, we know that titanium could be an issue. Not that I think there's a bunch of titanium in these waters because they are groundwaters, but, and sodium. And we did a bunch of tests with them and we didn't see much variation when we doped the standards with these things. So we can't even explain, even if you put highly elevated concentrations of either one of these elements in comparison to the copper that you're measuring, you wouldn't induce 100 per mil fractionation. That's just not likely. So then, another way of saying this is we looked at the total dissolved solid, and if you were having a relationship with that, you would expect a very linear trend with all the data. With the greater amount of total dissolved solid that you have, you would anticipate more highly fractionated values. And you can see the most fractionated value we have actually has some of the lowest total dissolved solid in it. So that hypothesis isn't that great either. So if the data are real, what do they indicate? And so we go through all these tests thinking, why are they good? Why are they bad? And said, well, we can't really rule them out just yet. So, so what do they indicate, and what can we see in them? And what I'm going to show you is that there's a clear spatial relationships with higher values that are much closer to the ore bodies, like we hypothesized there would be. There also appears to be some very interesting mixing trends when you compare the copper isotope values with chlorine, and well, copper isotope values and copper concentration, and then also copper isotope values with chlorine, and looking at the different types of brines that could potentially be there, and I'll point that out. And there also seems to be a depth relationship with some of these values too. So here's a map, and as you can see here, the red values, I don't know if they pop out too well, but the red values, trust me, are the higher copper isotope values, and they do cluster around Eloise and Jericho, and Marinon, which is down here to the south. And there are some higher outliers that don't have ore deposits around them, sort of right in the center, right above the north arrow. But there are known magnetic anomalies and other geophysical anomalies that might actually be occurring with. So here you go, there's Eloise and Jericho, and here's Marinon. So what's interesting here is if you then also plot this data versus the copper concentration, you can see that the ones that have the highest copper concentration have the highest copper isotope values. Now, when we say high copper concentration, it's not that high. It's about a part per billion. And these groundwaters, you can see the majority of them are down into the part per trillion range. So, the mixing relationship is, I don't think if you measured a part per billion copper in them, you'd really feel confident that you're looking at weathering of a copper deposit. But the layer of the copper isotope values in comparison to all the other copper isotope values around there sort of give you a little more, especially with this data set, security that it's there. And you can see that there's a very nice asymptotic trend there, or a clear mixing relationship. If I put the copper concentration 1 over the copper, you get a nice linear diagram there. It looks identical to what we saw at Pebble. And so here are the copper isotope values and then the copper concentrations. And you can see here the copper concentrations at Pebble were actually much greater. The lowest one, here it says 0, was about 6 or 7 ppb, which is 6 or 7 times at least more than the highest one that we looked at here. And then you have some that are in the ppm range once you get close to the deposit. And so you see, once again, that distinctive, if you look back here, right, those mixing curves are basically the same. So I would argue that that's pretty good evidence that this data might be pretty good. There's also, we see some relationships with depth, and maybe this is copper isotope values seeming to get lighter with depth. Maybe we're looking at different sources mixing, and with these different light sources mixing. So when we saw this depth relationship, we thought, well, gee, maybe we should try to look at general mixing diagrams with different types of brines. So we have chlorine concentrations. We have a bunch of geochemical data. We can fluoride it. And so we normalized with chlorine, and I put chlorine at the top and then copper at the bottom in my ratio here on the y-axis. I know chlorine's usually put on the bottom, but then the numbers became too ungodly small, so I'd rather have bigger than smaller numbers. That's just my arbitrary choice. And what you can see, there's 2 different trends to the data, where that you have a relatively low copper concentration source that has a low copper isotope value mixing with a higher copper concentration source with a higher copper isotope value. And then you have a very low copper isotope concentration with a slightly higher copper concentration in it. And so that's why you get sort of this dual array that I'm sort of showing you right here. So, maybe we're seeing mixing here, and maybe these data are showing us that by when we use other filters to look at this copper isotope data. And it's really amazing when you look at this data, because usually when we looked at the weathering on surface and oxidation of these copper sulfide minerals, the plot that I've got here on the top is a plot of different types of copper minerals that are weathering, and they produce this delta value, which is the on the x-axis here, which is simply the change and the copper isotope composition of the solution, which is heavier than the mineral. So positive values there indicating different weathering here of different minerals, because you can see waters that are weathering chalcopyrite usually give you about 1.5 per mil greater for chalcopyrite, and then those that are weathering chalcocite, which give you about 3 per mil greater than the surrounding waters when you're weathering the chalcocite. So it's neat, you can sort of relate mineralogy in this instance, and I pointed that out in the article we wrote in 2014 here on that top diagram. But then when you compare this to, what we, that's the 1 to 3 per mil variation. I don't know what that top blue box popped up out of error, but the bottom one is what I want you to see here, is that you can see, rather than just having 1 to 3 per mil variation, you're looking at like 2 orders of magnitude in each direction difference. So it might, if these values are true, it might even give you greater confidence that these data are they're real, but are they true? I think this might be a really an easy way to identify things, especially when you're trying to work undercover. Okay, so the take homes here is that our hypothesis that heavier waters due to dissolution of sulfide is further verified with these results. Even in the super low concentrations of the groundwater, it doesn't appear to limit the technique. And I started my career doing a lot of rhenium and osmium, and always trying to solve things at very low concentration in the part per trillion range is problematic, modeling and both thinking. So, one thing to think about is, are these values so fractionated simply because we're at such low concentration? So, and we're in rocks that have been weathered for a very long time. So I think, this is quite interesting, and one aspect of thinking along those lines in concentration also is something why these results might be so unique. It also might make it easier to measure on other instruments if these values are true, but then of course the sensitivity might be limited depending on what instrumentation you're looking at. Now, we need to really have more samples to hammer this out, and we have different ways in which we can process the waters once we dry them. And so we've been studying and found about 3 or 4 different new protocols that actually have just been published within the past 3 years of dealing with really briny or salty solutions and drying them down and then separating the sodium from the copper. So we're going to hopefully go back to these places, collect more solutions, test them using different techniques for separating them, and ultimately see how those compare to these initial results that we've gotten. And that's something that we need to figure out, because if these values are real, it really is amazing if, you know, there's this large degree of fractionation happening with these metals. And, you know, that also relates to why are things getting so light? You know, it's just sort of crazy. What is that meaning? And explaining that obviously be very important. Okay, so that's where I'll kind of stop. I wanted to leave some time for questions or comments. I think, you know, where I see things going here is we need to keep looking in unknown areas, because we just, the first time, looked at these groundwaters and you can see really large variations. So I think if we look at different hydrogeological situations, we might find even more interesting things. Vegetation I haven't really talked about, but I think there's a great potential for that to happen, because if the waters are doing it, the plants are just reflecting what the waters are doing. So I think that looking at plants, and we have some plant data, I didn't have time to go into that today. Soils could also be relating. Soils are going to be a little bit more complicated, I believe, because you have several different types of paths in which the metals could get fractionated, but certainly something to look at, and that has not been done. And then to get back to where I started the conversation with, I really do believe that we're at a point where you can start to do this comparative analysis and look at these larger data sets and then try to draw out some other interesting conclusions and interpretations of metal sources and what leads to the generation of these large metal concentrations on the surface of the Earth. And then the other thing I haven't really talked too much about is, in a vectoring sense, using different minerals. And here the talk is mostly focused on chalcopyrite and chalcocite, but we've done work with pyrite, more ubiquitous things, and also iron oxides, which are more common in holes that you're going to find with no ore in them, because that would be more applicable for those in the exploration sort of phase of things. So with that, I just wanted to finally thank you for your time and attention and acknowledge all these great entities that have supported this research.
I wanted to ask you, what are the steps that you see need to be taken to develop this technique, which is currently quite academic and expensive, into something that can be used as a exploration technique, and it can be used as a standard exploration technique, first of all. And secondly, how does this differentiate? How do the isotope, metal isotope, differentiate from just concentration? So if you go and measure waters for concentration rather than isotopes, isn't it much easier and quicker to target mineral deposits that way?
Yeah, so the first question—
Separate questions, but related.
Yeah, so the first question is cost and throughput. And so, you know, and then the second question is, like, what do the isotopes give you? So I think the isotopes give you a layer that the concentration won't give you. I'll start from the second question first and then work up to the first question. So like when I showed you the last slide about, you know, we can make inferences about mineralogy, and we can also then actually see presence of sulfide weathering, which you wouldn't have seen in concentration data at all. So if you looked at the data we saw from Jericho, you know, there was 3 values, I think, that sat above a ppb. The majority of them are in the part per trillion range. And so what that means is, you know, a lot of times when you're looking at these waters, they're not going to be much different from one another, at least in a concentration sense, to be able to make the call. The isotopes give you a layer to differentiate things that are relatively similar concentration, but could have a distinctly different copper isotope ratio, because that copper is derived from the weathering of the sulfide. So that's why you'd want to do that and add that layer. And then the second question is about the feasibility for industry, and how can that work. And so yeah, it's not as routine as a concentration measurement, and there's no doubt about it. There's still, you know, we are still trying to work on techniques to get it become more cost effective. But I think what the information you're getting, you don't necessarily always have to run 500 samples, right? Depending on your sampling protocol or what you're doing. You could take a subset and it could give you some ideas. And you might be able to use the concentration data to help you cherry pick out what you'd wanted to use the isotopes on. And then that could give you a way to dive into a certain place if you got a subset of data, and then use that to then expand into another area. So there's strategic ways in which you could use the concentration data that you have and still work within the constraints of whatever your budget may be. But I mean, if you look at this data here in Jericho and you look in that basin, you could argue you could go solve out pretty quickly where a lot of these places would be with less than 100 or so analyses, right? So I think that the technique shows itself pretty clearly. And so I'm not gonna, I don't know what the right word is, apologize for the cost. I don't want to say it that way, but I want to say, you're getting something different, right? And so, and you can use it in a way, and it will give you a competitive advantage, right, than the way everyone else has been looking at it. I mean, look at this. We measured groundwater, did one groundwater study that I've been a part of, because I've measured lots of copper isotope ratio stuff. Look how fascinating the results are. And I just think, we're like, once you start getting more and more of this stuff, it'll become more commonplace simply because of the success of previous studies. That's why I see it going.
All right, thanks very much. Hey, Ryan, can you switch off your share screen?
Oh, sure.
If you don't need it, at least.
No.
Just read out the questions as they've come in, and we'll start with the first one. And as you switched off the share screen, my carefully prepared chat page also disappeared. I don't know what happened there.
Okay, let me see. Oh, so I see Joseph Tank. Have you compared isotopic data from groundwater to potential underlying ore systems, or how closely do they match? So when we did the Pebble work, we had exact distances from the known ore bodies. So we could say within about 2.5 to 3 kilometers on those surface waters, we could see quite that signature quite easily. In comparison, in Butte, Montana, where we did an environmental study, where obviously they've exposed the ore there, you can get a little bit more, upwards of 5 to 6 kilometers from the deposit. But you also had, they're belching out sort of all sorts of processing of the copper fine particulate matter. So that might be why we're able to see things a little bit farther distance from the ore body. But think about probably 2.5 kilometers. I think it has everything to do with mixing of when you see the water that mixed with the sulfide with the other, the waters surrounding there. And that's going to control the aerial that you're going to be able to see. Okay.
What the implications of the University of Alaska US patent on the use of mineral isotopes in water for other laboratories looking to undertake this work?
Yeah, so we when we wrote the paper, the University of Alaska, I worked with Leanne Monk, and her institution wanted to patent it. So the work was done with them and the patent was done with them. So I'm not a patent lawyer, so I can't really speak to that. So I apologize, but I can certainly get you in touch with people that can work with this. I do know that the patent's exclusively in United States properties, right? So if you're doing it in the United States, that's where the patent holds. It's not an international patent, I can tell you that. So and from that, if you have, I can get you in contact with the U of A, University of Alaska lawyers. They know how all that works. Like I said, I have not paid too much of attention to that patent.
Do you know what is patented, Ryan?
So the idea is that if you find the heavy copper isotope signal and that leads to a mining activity, that's what's patented. So the action, the key thing is there wasn't patenting of an isotope value. The actionability was if it leads to actually a mining activity derived from use of the copper isotope values. So they're a twofold thing there. It's not just anyone can measure. It's not measuring copper isotope values, or you have to worry about that. The point is if it leads to the finding of an ore body, it's that action that is patented. So all of these waters, we're looking at dissolved copper and they're filtered. So any particulate copper or large amounts of organic compounds associated with the copper, well, I guess they might slip through some of the filtration, but most of that stuff is picked up in the filter and then dissolved. We have done studies. There are several studies with where microbiologists have isolated the different organisms. The first study we wrote in 2005, we did a really detailed study of Thiobacillus ferrooxidans, and we isolated them from waters. We grew them and isolated them, and we looked at their copper isotope content, and they did fractionate copper to some degree, but the concentration of these bacterium in the solutions are usually low enough so that it didn't seem to be what was causing what we were seeing. So I'm most of the time when I look at this data, I think of it in terms of dissolved inorganic copper. I don't see it as organically bound or fractionated because of organics. That's usually how we see, or how I interpret and how we try to sample.
Are there any more questions or comments that people want to place and ask from Ryan?
Hey, Paul, can I ask Ryan a question?
Yeah, go for it.
So Ryan, this is probably unrelated somehow, but in pollution studies of groundwater, people usually identify that there is a certain direction of groundwater flow and the pollutant is traveling like a plume along that direction. Why would that not happen with copper isotopes? Why would they be?
Yeah, it surely would. Yeah, I mean, the pollution source is a constant, I guess, in these systems, you can think of it. So yeah, it is traveling. I don't know if you'd see it as a plume because it's the source of the copper mineralization is, and that relates to, you know, how far away can you see these things? I think that's sort of a question. So you can see the copper isotope signature emanating from, in a subsurface sense, you know, that's what I was saying, in like several kilometers away. But yeah, I see it that way, sort of like as the way you're describing.
Thanks.
Mm-hmm.
All right, thank you very much, Ryan. I think we'll leave it here. It's been fascinating. As I mentioned, we're working currently with Ryan to develop these isotope systems here at JCU. And if people are interested in finding out more or working with us, the person to contact here at JCU is Brendan Mahon. And if you're interested in any projects in this, let us know as well. In the meantime, Ryan, thanks very much for making your time available. I know it's a big time differential. And thanks very much for your time and doing this for EGRU.